In this video, we're going to take a deep dive into the ExScan software from Shining 3D and learn about the different scan modes, settings, and options, so stay tuned. Hey everyone, this is Matt with Learn Everything About Design, and in this video, we're going to do a deep dive into the ExScan software and try to cover all of the various options that we have. The first thing that we want to make sure that we understand is we're going to cover four main areas: the scan modes. We're going to also talk about the scan settings in each of those modes, the mesh settings when we're converting our point clouds to mesh, and mesh processing options. But the first thing that we need to cover are going to be the scan modes. We're going to first talk about the three options, starting with fixed scan. Fixed scan is where we place the scanner on a tripod and do either a single or turntable scan. Handheld HD scan is where we're going to be holding the scanner and moving it around our stationary part. Handheld rapid is very similar, but there are some unique options. We're talking about the differences between a handheld HD scan and a handheld rapid scan. Once we start to talk about each of these, we'll discover the differences between them, but the first thing that we want to do is we want to begin talking about a fixed scan. So let's take a look at what a fixed scan looks like. In all of these, we're going to be using the non-textured option, and we're going to focus on just the specific settings. When we're doing a fixed scan, the settings are on the left-hand side. We have a handful of things that we want to understand. The accuracy of a fixed scan is fixed at 0.04 millimeters. This is the highest of any of the options. The point resolution is also fixed at 0.24 millimeters between points. Single scan happens in about half a second, and our alignment options allow us to use turntable targets, assuming we're not covering them up. We have feature alignment, marker alignment, or manual alignment. Now, all of these options are important because it will dictate how we can use the various turntable options. For example, if our part is too big for turntable targets, we must use features or markers or even manual alignment. Inside of our scan settings, we also want to talk about brightness, HDR, and turntable. Brightness is very similar to all the other scan settings, but the HDR option that we have here is unique and allows us to take a look at low and high brightness each scan. It's great when you have high contrast objects. We also have a toggle to turn on and off the turntable. We can use the fixed scan with a single scan, manually moving our part and then manually aligning them. It is much easier to have a small part that fits inside of the center of the turntable, and you can use those coded markers. Going through the manual process to align each of these objects and scans can be a bit tricky on certain types of parts. Next, let's take a look at our handheld HD scan. Again, we're going to talk about the differences between HD and rapid, but for HD scans, we first want to focus on any unique details here: alignment, operation mode, and resolution. When we're talking about the mode of alignment here, we're talking about hybrid, which is a combination of markers and features. Markers, which are adhesive reflective dots, and then features. If we have prismatic parts with a lot of unique complex features, this option can be used. When we're talking about the operation mode, we have classic and high detail. Classic is 10 frames a second, and high detail is also 10. However, it does give us more detail, but reduces the distance that we need to be away from our object. And last, we have our resolution. This is going to determine the distance between the points in our point cloud, which ultimately get converted into a mesh. This has to be picked before we do our HD scan, and we can have options anywhere from 0.2 up to 1 millimeter between those points. This is going to come into play as we take a look at some of the other options in other scan modes. When we take a look at a scan that's created using the handheld HD mode, the brightness is set after we start the preview of the scan. We need to take a look at our object, and we need to begin adjusting the brightness until we just start to see a red appear on the lighter areas of our design. As we look at the preview on the screen, we can see that there are certain areas that are starting to show that red highlight. Now, this is basically the saturation of the model. You want to make sure that it's not too red or it's not too dark, otherwise you will have problems capturing that scan data. This also does change depending on how far away the scanner is when you're talking about the distance between your object and the scanner itself. Remember, if you're using the high detail mode, you need to be about half of the distance you are on the traditional classic mode. Next, let's take a look at a handheld rapid scan. We're going to talk specifically about the differences between the rapid scan options and the handheld HD scan. We still have our selected mode of alignment, but it's important to note that HD is 10 frames a second, while rapid is 30. The HD captures 3 million points per second, while rapid is only 1.5 million points. The alignment options are still very similar. The operation modes are different here for our rapid scan. We still do have a classic option, but now it's capturing more frames per second than our handheld HD. We also have a lightning option and a lightning plus refine. Now these have some unique differences between our handheld HD. Classic is now at 15 frames per second at the selected resolution. Lightning is capturing at 30 frames a second at 1mm resolution with an interpolation. And lightning and refine happens at the same 30 frames a second, but the interpolation happens at the resolution after the scan is captured. This is important because it lets you capture data relatively quickly, and afterwards you can determine what that resolution is going to be, anywhere from 0.5 millimeters to 1.5 millimeters. Keep in mind that is an interpolation that happens, which means that it's fitting points in between other points. You might possibly lose some detail, and this is why the rapid scan has the lowest accuracy and the lowest resolution of any of the other options. So this is great if you're capturing big objects that you don't necessarily need to go down to 0.04 accuracy. So if we take a look at using these options, we're going to be looking at this in real time so we can better understand how quickly it captures our data. In this example, we're looking at scanning a transmission using markers and features on the object. So this is a hybrid alignment using the lightning plus refine. When we do this, you can see that in real time, it's doing a great job of capturing everything, all of the data on this design. It does have a handful of markers, but it is mainly using feature alignment for most of the transmission. Now, I was really pleasantly surprised with how well it captured data using this lightning plus refine method. Once again, we are using 30 frames a second, which is quite a bit of data coming into the software. We are using a resolution of 1 millimeter, which downstream gets interpolated. And again, what we're doing here is if we're going to a lower resolution, say 1.5 millimeters per point, then it's actually going to reduce that. It's going to spread them out. If we're trying to go to a finer resolution, it's going to try to fit points between what we have selected. So it is important that we understand the accuracy is going to suffer, but we're still looking at plus or minus 0.1 millimeters for that accuracy value. If we contrast that with the fixed scan at 0.04 or the handheld HD scan at 0.045, it is quite a bit different than those two options. But again, depending on the object that you're scanning, if it's a large object, if you aren't required to have quite as much resolution or detail on it, then it could be a great option to capture that quickly. For me, something like this transmission, this is a perfect option. It's going to get me close enough to the data I need for the purposes I need this mesh model for. So I think it's a great option to play around with these different settings whenever you're using the scanning modes. You can see here that after we're done scanning, we then get to pick which resolution we want. In this case, I stuck with the 1 millimeter, and then I didn't have to really worry about the interpolation. I did use this with 3 individual scans. I aligned them after the fact, and then used the meshing options with a low filter and a medium smooth. To better understand what these mesh optimization settings are, let's take a look at a different model. In this case, we have this dragon model that I scanned. It was relatively high detail. I did a turntable scan, getting the highest accuracy of 0.04 millimeters, and again, the point resolution was 0.24 millimeters between points. What we're doing here is we're beginning by doing a global optimization of the 2 scans that were aligned, and once we have our global optimization, then we can turn this into actual meshes. Now, the way we generate the mesh is there's 2 steps to this. First, we need to determine the initial mesh optimization settings. This is going to be a somewhat destructive process. Once we confirm this is the starting point for all of our mesh edits, we're going to turn the filter off, no smoothing options, and take a look at the results. To better understand what's happening, let's take a look and compare some images. In this case, what we have is all of the filter options. We've got a low option across all 4 images. The smoothing options are currently set to none on the left image, and then we go from low, medium, and high as we move to the right. What we want to do is we want to identify different areas of the design and how these different smoothing options are going to affect it with a low filter. When we think about filter and smoothing, we want to think about what's actually happening underneath the hood. Filtering is taking a look at the current mesh that we have created, and the filter is going to be taking a look at high and low areas, and a low filter is going to be less destructive, leaving more of the original mesh in place. To better understand this, let's point out a few areas on this design. If we focus our attention on this part of the neck, we can see that there is one area where there's a little bit of a dip or a pocket, and then there is a sharp edge on the end. When we look at the original part with no smoothing and no filter, and as we move through to the medium and the high smoothing, we can see that there is a definite difference in this area. Once we go to a high smooth, it actually gets rid of the little dimple or divot that's there in the low and partially in the medium. So with these low filter options, the low, medium, and high versions of smoothing do drastically change the end result. Now keep in mind, what we're doing here is we're actually looking at just a figurine, a little dragon scan. But if we start applying this to our mechanical parts, maybe we're looking at ribs on a cast part or specific features that are important details for us, those features can start to get filtered or smoothed out if we're not careful with these settings. Generally, I like to use no filtering and smoothing on the initial mesh, and then I can process it downstream if needed. But in a case like this dragon, let's take a look at what happens when we change the filter from low to medium. Now we still have no filter and no smoothing on the left-hand side, but now we have various options for medium filters going from low, medium, and high on the smoothing. Once again, what we want to do is we want to point out a specific area and see how it changes when we change each of those filtering options. So if we look at the image on the left, right underneath the neck, you can see there is this bulge here. Now it's pretty pronounced on the unfiltered and unsmoothed design. When we move over to the medium filter with low smoothing, we can definitely see this design comes to more of a peak. It's more of a rounded bulge. As we move through to our various options, medium filter and medium smoothing, this starts to get a more pronounced edge and it becomes a little bit bigger and flatter. Now, once again, the smoothing is actually taking a look at increasing the mesh density to smooth it out. As we go to a high smoothing with a medium filter, it takes that original neck bulge on that original unfiltered and unsmooth design and changes it quite a bit in just a small number of steps. So once again, these options are important to understand that filter is looking at the original mesh elements and it's determining how it can spread those out, and smooth is actually increasing the number of mesh elements to increase the smoothness. Next, let's take a look at what happens when we set the filter options all the way to high. Once again, this is going to be the most destructive, changing it the most from the original mesh. Now, with the filter option set to high on all of these images, let's talk about the low, medium, and high. Once again, we want to focus on a specific area. In this case, let's take a look at the second notch down on the neck. There's a little bit of a secondary bulge that happens on the initial design. Now, once again, the high filter is the most aggressive, which means that it is taking a look at all the surrounding points and it's going to spread them out. Think about taking something like shrink wrap and stretching it over something. What we're doing is we're essentially smoothing and stretching it out. And as we move through to the low, medium, and high smooth, you can see exactly what's happening through each of these images. There is less of a change in the low, medium, and high smooth options when the filter is set to high in these cases. It's less apparent. But it is important to note that the difference from the initial unfiltered and unsmooth design to the low, medium, and high smooth design with high filter is a somewhat drastic difference, at least in this design. It is going to depend on your initial scan. To better piece this together, let's take a look at one more image. Now what we have here is the smoothing set to high on all of the images, but now what we're doing is we're changing the filter settings from low to medium to high. So here we can see that the high smoothing setting is going to increase the number of mesh elements that we have, but the filter is the main thing that we want to look at as to how that actually changes the design. So let's go about halfway down the neck and take a look at this area on the unfiltered and unsmooth design. As we move through to the low filter, high smooth, there is a very pronounced secondary bump that happens in this area. We can see the two high points based on the highlights of the mesh. But that doesn't mean that this is the best option for us. We just simply want to identify what a low filter looks like with high smoothing. Now, as we take a look at this, let's move over to the medium filter with high smoothing. The secondary bump is starting to disappear in this case. And once again, the filter is taking a look at the highs and lows in the initial mesh, and it's sort of doing an average. It's taking those and it's saying if it's low in this area, it's going to raise it up. If it's high, it's going to drop it down. And that's based on the surrounding mesh elements. If we move over to the high filter and high smooth, you can see now those 2 points are completely gone. It's just a single edge that happens here. And once again, it really depends on your design. So if you're trying to understand these settings, you can always hit the reset or undo option when you're looking at each of these settings. And I think it's a good idea to do this as you go through various scans. Set your filter to low, medium, and high, and do a high smooth and just get an idea of what it's doing and what is changing in your design. Now, as I mentioned before, if I'm looking at reverse engineering a part, generally I will do either no filter or a low filter, depending on how clean or noisy the scan data actually is. In most cases, I like to have the original scan, whether it's noisy or not, at some point. After this step in the process, after we determine what our filtering and our smoothing settings are, at that point, we can save out the actual mesh before we do any other mesh manipulation. We can save it out even though it's not going to be aligned to a coordinate system and have that as sort of a starting point. But these settings are going to be the first settings in the creation of the mesh from the point cloud. So once you change this, you can't go back to that original mesh. You have to go back to the original points. This brings us to the next step in the process, which is mesh manipulation. Now, after we've created the initial mesh, what we're going to be doing is taking a look at the options we have to further process it. In this case, we're going to start by talking about simplification, which is going to decrease the mesh element count based on some settings that we manipulate. Then we have mesh optimization. This is actually going to increase the mesh element count in certain areas of high curvature. We then have a smoothing option, which is going to take the statistical average of the position of mesh elements. If we have a large flat surface, for example, it'll help to smooth those out. We also have remove small floating parts. If your mesh has made it this far and there are disconnected areas, this will help us easily remove them. We also have an auto hole filling option, which will look at the perimeter size that we specify and automatically fill those holes. We also have manual hole filling, which allows us to select openings on the mesh and fill those. In this case, we can use things like a flat or curvature-based fill. All of these options can help us further process the scan data. So let's take a look at the way in which we would typically do this. Now, not doing this necessarily in order, but generally what I would do is I would start by selecting certain areas that we no longer need on the mesh and begin removing and filling those. For example, on this scan, there was a small sticker on the bottom. So by selecting and deleting that, I now can go back and use tools like manual hole filling to fill that in. The problem that we typically have with something like this is there are going to be potentially small areas that are left behind. We can see the two green areas. Those are actually elements that are now disconnected from the rest of the mesh. We can go back in and try to use the manual hole filling and fill in those areas once more, simply by selecting those two green areas and making sure that the filling type is set to whatever we need. Because this design was ultimately 3D printed without any further processing outside of ExScan, the main thing was that I wanted a flat bottom. Another way that we could do this is by completely removing the entire bottom of the mesh. This allows us to remove any and all elements, then go back and use things like auto hole filling or manual hole filling. Remember, the auto hole filling is looking at a perimeter size, so if you don't have a consistent perimeter, that can be a little bit tricky to use. It's great if, for example, there are marker holes that were left unfilled. In this case, manual hole filling makes the most sense, and using a filling type of flat. This will bridge or blend around the corners for us, but keep a relatively flat base on the bottom. Now that we've done a little bit of a manual processing, next is to go into our simplification. Now, the way that simplification works is it's going to take the number of elements that we have in our design, and using our simplification slider, it'll reduce those. Now, it's not necessarily a one-to-one ratio with the slider, but you can think about it like this. If you have 10 triangles on your mesh and you're setting the simplification to reduce it down to, let's say, 50%, you're going to end up with 5 triangles. In this case, if we go all the way up to 99, we get an extremely low poly version of this dragon. Now you can see that it drastically reduced the size of the file, but if you're scanning something with high detail, that's probably going to be too much. You need to play around with those options. Next, we have mesh optimization, and this is actually slightly different than simplification because it's looking at areas of high change in curvature, things like sharp corners or fillets on the edge of a mechanical part. These areas are going to have an increased number of triangles or mesh elements, and this mesh optimization allows us to have higher densities in areas of high curvature and lower densities in areas that are relatively flat. Once again, you need to play around with these settings on your designs. The smoothing option is looking at the statistical average position of these triangles or mesh elements. If you have a part that should be relatively flat, but there are a bunch of high and low spots, you can use smoothing to help average out those spots. In this design, we also have the remove small floating parts option, but there aren't any floating parts here. This is great if there happens to be anything small left behind after some manual deleting and repairing. In this case, everything is fine, so we can cancel or confirm. Both options will give us the same result. So remember, at any point in this process with simplification or optimization, we can save out a version of that mesh by using these save options. So after you play around with your designs and better understand what these options do, then you can move on to the next step in the process, which for us is going to be moving into measurement. For that, let's take a look at a slightly different model going back to the transmission scan. The next step in the process that we want to talk about happens after you've created your mesh. This is the measurement process where we create features such as points, lines, and planes, and we use those to align our mesh to the coordinate system. In this case, for the transmission, we want to create a couple planes, in this case on the front of the bell housing where it bolts to the back of the engine. We use 3 points that we feel are accurate representations of the part. We select create, and now we have a plane that creates a reference on the front of the bell housing. I'm going to create a second plane that's in the area where the shifter bolts to the back of the transmission. Now, this scan data, based on the scan itself and some of the smoothing settings, you can see is probably not the best representation of a flat plane. However, I do know that this is flat relative to the ground, so I'm going to create another reference plane and use that to create a line as a plane-plane intersection. This should give me a good reference on the front of the transmission that will allow me to see what should be X or Y direction. Once we've created a plane and a line, we also need a point which is going to be the reference location for XYZ0. Now, in the case of this transmission, I'm going to do my best to grab a point at the center of the input shaft to the transmission. If I decide to reverse engineer this or use it for, say, creating some components, that'd be a good place for me to have my reference. Then, in the movement section, we can use 3, 2, 1. Select the plane, in this case the plane that's on the back of the engine or the front of the bell housing. I'm going to set it as my Y. We have a constraint line and the point again, which is going to be XYZ0. If any of the orientations are incorrect, we can make a change in the dialog, for example changing X minus to X plus, and now we can see the orientation of the transmission based on the view cube that's located in the bottom right. So at this point, this allows us to save this mesh file and it'll be aligned to XYZ0 with that 0 point at the input shaft of the transmission. Now let's talk about some best practices for things like marker dots and model prep. When we're talking about using marker dots or the adhesive reflective stickers, we want to make sure we understand how many are too many, how many are not enough, and what's kind of a good result. When we take a look at this fender, this is essentially too many marker dots for a couple of reasons. We want to make sure that we have at least 4 in view of the scanner at all times. But what does really 4 mean when we're talking about in the scanner view? When we take a look at the door of the car, there are 4 dots which are essentially in the scanner view, but these are pretty far spaced away. Now, when we take a look at what's happening during a scan, this leaves a pretty large light pattern on the car. However, the actual view of the camera is much smaller than that. And in this case, there's only one point that's seen by the camera in this area. This means that this number of marker dots is not quite enough for us to use accurate alignment during the scan process on a large flat part. When we go to the rear fender, this is one that has a pretty good spread of dots. You can see here that we've got 4 in a relatively small area that are all going to be seen by the scanner at the same time. Now, there's another important factor here is we need to make sure that these are randomly placed. If these are set in some sort of pattern, the scanner is not going to be able to accurately tell where along the car or the flat panel it is. So we need to make sure that they're close enough together, but they're randomly spread out. If we have too many marker dots, what ends up happening is the system can start double counting those, and we end up with misalignment in our mesh. Now that we've taken a look at marker dots, let's talk about the last step in this process, and that's prepping your parts. Now, a couple of different things we talked about in some previous videos. Shiny black parts like this anodized part, these are not good. The scanner is not going to pick those up at all. However, primered parts or parts that have a flat finish, these are great for the scanning process. These are really well received by the scanner. We get great data off of these. However, we don't necessarily want to paint all our parts, so we also want to talk about what other types of materials or finishes are okay. Well, generally shiny parts are very difficult, but in the case of things like cast aluminum, such as this brake lever, these scanned pretty well as is. We didn't really have to do much to prep this part. So as we're thinking about the parts that we're going to be scanning, we need to really understand the surface finish and whether that means that we need to prep the part, potentially paint the part, or do something else. So once again, parts like in this case, the bar mount, these are great options. Flat finish scans really well. Shiny parts like the triple clamp, not so great. So the last step in this process is how do we prep them? Well, spray paint like we did with the bar mount is a cheap solution. We can prep and paint the part. However, paint removal can be kind of a pain. These are not time sensitive, which means once we paint it, we can scan it at any point in time. The next option is something like a weld inspection spray. This is a bit more expensive, generally about $20 a can. Requires cleanup, it's a bit messy, but it's not time sensitive. Once you spray it on the part, you can leave it. You just have to be careful handling it because you can smudge it. The last option is a dedicated scanning spray. These are generally close to $40 a can, but they require no cleanup. You spray them on, they're generally good for about 1 to 2 hours. Within 4 hours, they will completely dissolve and be gone, so it is time sensitive. So you really need to think about what you're scanning, how big it is, and how you need to prep it. So let's talk about some of the last things like a scanning checklist. So whenever I'm getting ready to scan a part, there are a few things that I think about. The first of this is the part size. If I have a relatively large part or a really small part, that'll determine whether or not I'm using something like a turntable or if I'm going to be doing handheld HD scan or a handheld rapid scan. These will also help us pick some of our scan settings. The next thing on our list is features. Are the features on our part critical? Is this something that we need to capture and we need to be extremely accurate? And again, that's going to point us in the right direction for things like our scan mode and some of the settings that we use in those modes. Next on our list is going to be surface finish. Does our part require surface prep? Are we going to have to paint it? Are we going to have to use a weld inspection spray or a dedicated scan spray? And based on the part size and the features, this could cost quite a bit. And last is the downstream processing. We need to know what we're going to do with that scan data. Are we trying to reverse engineer something? In which case, do we need those critical features? Do we need a high resolution mesh? Or is it going to be a loose reference for something? Do we just need to have that mesh data as a reference that doesn't necessarily need to be extremely accurate? Can we use a handheld rapid scan with the Lightning plus Refine option to capture the data as quick as possible? Or do we need to use something like a turntable with 0.04 millimeters resolution? All of these various things are going to determine things like whether or not you use markers or feature alignment, whether or not you need to prep your part with a surface spray, or whether you need to scan it or at all. So now at the very end of this, we should have a pretty good understanding of nearly all of the settings and options inside of ExScan Pro. If you have any questions on this or anything else, please let me know. You can always reach out by email or leave a comment in the video. As always, thanks for watching, and we'll see you next time.